Hello, everybody. In this lesson, we are going to continue looking at projectile motion, and we're going to look at we're going to start out with a simple case of horizontal projection. So just to remind us what we've seen recently, the idea of horizontal and vertical velocities being independent of one another. This is what we're working towards. And so if you look at this sequence of pictures that we're taking at equal time intervals of a pretty awesome jump here going on. What do you notice about the horizontal spacing of those? If you look at the horizontal spacing, line them up, roughly speaking, with the center mass each time or whatever, right? Nice and even spacing. And then what do you notice about the vertical spacing? Vertical spacing works about there, I guess. So you see how it's changing, right? So the equally spaced time photos show that horizontal velocity is staying the same the whole time once it's launched, right? Obviously, if the gas is on or off here, it's going to change the horizontal. But once it's launched, there's nothing to propel it or change its velocity horizontally. But there is something to change the velocity vertically, which is, of course, gravity, right? So the vertical, you can picture it going up slower and slower and then back down faster and faster, but just stretched out over time, right? So you can see that the horizontal velocity is constant. And the vertical velocity is accelerating due to gravity. All right. So that's, we're going to want to be able to work with this. But the key to being able to work with it is to recognize that we can separate these two things out and complete them or treat them completely separately. Yeah. So, like the programmers for this game you might have seen and heard of or played in the past or whatever, obviously they'd be doing calculations to map out the path that the very angry bird would follow. So we're going to work towards that. And to get to it, we're going to look at horizontal projection first. So what is horizontal projection? Horizontal projection is just when something is launched straight sideways. So it simplifies things a lot, right? If you just drive off of a ledge, you would just travel and fall down rather than going up first, and that makes it a bit easier for us to deal with. So I'm just going to analyze what would happen here. So if a steel ball was just dropped straight down, and it's the same type of steel ball, doesn't matter, of course, mass doesn't matter, right? We learned that recently. We'll see more about that coming up as we go through the course. But you can picture that the steel ball that's just dropped might have a path, something kind of like that, right? Just boom, 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 straight down, accelerating as it goes. The one that's launched sideways is going to have, a constant velocity sideways as it falls. So what we can do is we can predict what would happen. That this ball would still fall down to that height, right, as it travels sideways, and then it would travel sideways the same amount again and fall down to the same height as the other one. The idea is that this ball is falling freely under the force of gravity, just like this one. It just also has this horizontal velocity, right? And so you can actually map out the kind of path it would have, and you get this parabolic trajectory just because of the vertical velocity accelerating and the horizontal velocity staying the same. Okay, so that path that we mapped out there is very familiar. It's like, the kind of path that a ball would take if just launched sideways and allowed to fall freely under the force of gravity. It's a simplified version of projectile motion. All right, and so basically we can predict this, like what, sorry, I guess I should have asked, but I think it's pretty obvious, right? Like when it says, which one will hit the ground first, right? You tell that they're both falling towards the ground at the same rate. One's just going to land further sideways, right? So they're going to land at the same time. The fact that one's traveling sideways while falling does not change the time that it takes to fall. So hopefully that seems logical to you and you're good with it. If you need more proof, we can load up some videos that I just made recently here. I need to just move this one, get over. I guess I just have to make it go behind or something. Do this. Order. Send back. That way I can click on my link here. So the link, this link brings us to a video where I have a little device here that launches one ball sideways. And so launches one ball sideways. It's like right in here somewhere. And it drops the other one straight down. And honestly, we'll learn more about why that is later, but I can show you a close-up of it later, but there's no point right now because we haven't learned about inertia and the mechanics of that kind of thing, Newton's laws. Okay, so for now, just know that this thing is dropping a ball straight down. That's the ball there, and it's launching. It's hitting another one straight sideways. Okay, and I made it as level as I could. And so basically, I'm giving this one a sideways velocity, and this one just getting dropped, just like we're talking about. So you can watch the video and see how it looks, right? So, and listen, by the way. Watch and listen. I'll turn the volume up a bit. Hear how they land pretty much right in unison. One landing right around here, the other one landing over here somewhere. I'll play it again. It landed right over here. Okay, so hopefully you can see that well. I don't see why you wouldn't be able to, and you can click on the link yourself and see it full screen as well, of course. Yeah, and so, seeing is believing here. Just do a slow motion one. Oh boy, that's not what I wanted. All right, here we go, slow motion. There's the ball, falling, and so on. Exactly like we mapped out, landing within reason, the same time. Like I said, I made it as level as I could. Oh, there they go. One's coming down here, coming there, boom, landing right in unison there. So that should be pretty convincing. It's a nice little demo, and actually kind of nicer actually having a video version of it rather than just doing it live in the class. If you're interested, this link here shows how you can make a device just like that on your own. It's called a free fall flicker, they call it. Videos, fall flicker. So this little physics activity of making a free fall flicker, pretty easy to do. You just need a popsicle stick and play easier for us. So basically,
look at the two balls in this picture.
They're talking through it and so on. They don't actually even answer the question here, but this is the idea. You have a popsicle stick and a piece of paper folded around it. You have a penny sitting there and a penny sitting there, and you can pull it back because of the popsicle stick, and you can fling it, right? And so you fling the one coin sideways, the other one just gets left behind. We'll know later on because of inertia. But yeah, so one penny drops, one goes flying sideways, and you can see for yourself that it works. Okay, so there's no tricks going on. You can just check it out. There's applets that I've used in the past, but they killed Flash. Apparently it was not secure and so on, but same idea, right? One going sideways, one dropping, landing at the same time. There's nice simulations that you can use to show this as well. So in this one, all you have to do is change the angle to be 0, right? And so if I start this one, and I make it go sideways with 5 meters per second, you can see it takes 1.01 seconds to land. And then I could reset it and change the initial speed to 0 and start. And so that 1.01 seconds, boom, shows up again. Basically the ball dropping and the ball launching sideways takes the same amount of time to land. If it's level, if it's launched heavily horizontally and so on, horizontal projection. And if the ground is level, of course, too, right? This little applet here is a similar idea, but I mean, same kind of stuff. It just doesn't quite work. I wish he had this is a guy that I met at a physics conference, and he had a whole bunch of applets and all that. And so I was just trying to use his to do this as well. And so you could launch it and say, okay, it takes a certain amount of time. So I'll just slow it down a little bit so it lands on the page better. So 1.28 seconds, right? So just get a feel for like, boom, boom, lands, right? And then if you can change that speed to be 0, I wish he had it working properly, but you drop it, boom, boom. It's the same time. Okay, he just unfortunately doesn't have it programmed to actually state the amount of time. So I just thought I'd show it to you multiple ways. The extreme case of this is really hard to fathom or believe. it's really just because we're used to guns firing bullets like up in the air, and of course they take a long time to come back down because they go so far up in the air. But if you fire a bullet straight sideways, drop a bullet straight down at the same time, they actually will land at the same time if it's level ground. And so this is a thought of as a possible myth, right, amongst people, because it just seems odd. And so MythBusters actually checked it out and confirmed it. I will play a little bit of it, but I'm going to have to be careful, I think, for copyright business issues here. But bullet fired versus drop, MythBusters. So bullet fired versus dropped, and so I'll try to get away with this here. Want to play for me? I think this is sort of the flipped result of this.
Is needed to match the soul.
So we just go through here. They've got a gun on a system. They hit it, they shoot it. It's designed to like be able to recoil back, I guess. I don't know why they should have just mounted it more firmly, but maybe. Anyway, so he zips down to the end of the warehouse to see the slow motion replay of things. And
all right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
So they've calculated the speed of the bullet, and then they've put the camera and so on where they think it's going to land based on the horizontal velocity they know it's going and the height it's starting at. And so he's like predicting, be like, oh, it's going to work first try. And he's like, are you
never
serious?
make predictions. That's awesome.
Bullet dropped versus fired. In 3, 2, 1.
So jump ahead
where
to
the fired bullet landed. Let's go see where it hit. So Adam takes a one-wheeled ride down the room to check out the drop zone. Wow. And the results are simply ripping. Can't get much closer than that.
So there's the bullet that just dropped.
I can't wait to
There's
see
the
high
mark
speed
from the bullet that landed.
So, dude, this bullet carved the streak right under the drop zone.
There's the one landed and one that hit. Right? Pretty awesome.
The shot we've been looking for. In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers. 3677 minus 3915 equals 238.
So long story short, he calculates it out, and it landed like they're off by like 0.000. It was very, 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 very close landing time. Pretty neat. Hopefully, I get away with that. Otherwise, I'll have to just put it on my not leave it on YouTube or whatever. But you'll still see the video anyways because I can put it in the D2L system directly. So what we can do with this is we can use this as a simpler case to start working on projectile motion stuff. And so we're going to be given information here. The bullet's launched sideways at 5 from a height of 2 meters. How long it takes to land, how far over it lands, and the velocity it hits the ground with are all things we need to be able to calculate, right? So if you look at the given information, we're given the sideways velocity, we're given the vertical displacement, we're given the acceleration in the y direction. We're also given the vertical velocity is 0. Added that in as an afterthought, I guess, because it's kind of hidden information, right? So the acceleration is hidden and the initial vertical velocity is hidden. So in part A, we're looking for the time it takes to land, so we have enough variables to figure that out. We just have to think of how we do that, right? Isolate the situation. Basically, you're going to need to focus on the vertical situation. So this right here, we're going to use vertical information, and vertical information in order to answer this, right? So it's going to be vertical stuff that we're going to deal with there. And then this is going to be, of course, horizontal. And so we're going to use the horizontal information to figure this out, okay? So that's how it's going to work. So determine how long it takes to land is asked first, but of course we need to do that because we know how far falls, right? And we know its initial velocity, we know its acceleration, so we actually have enough information to be able to figure this out. The picture is pretty obvious here, right? Just looking at a physical graph of the situation. I'll of course go and show like a VT graph of it as well, whereas you have this initial velocity of 0 and it accelerates and so on. If you look at the area and the acceleration, you end up with two equations, two unknowns, because you don't know how long it takes to land and you don't know the final velocity. So instead of that, of course, we can go ahead and do the equations, right? So if we pick the equations from our situation, we've got the vertical situation going on for time, right? So we're looking at V1 is 0, V1y equals 0. We have the acceleration, and we have the displacement, and we're looking for the time. Okay, and so that means we can use this one. Now, you have seen in the past this lead to a quadratic, right? But in this situation, we get kind of lucky because the initial velocity is 0. And so we can actually just plug numbers in and solve directly. So notice here, we don't have to solve a quadratic. And so this is totally fine, right? If V1 wasn't 0, then you're probably going to want to get V2 first instead of having to solve a quadratic. So just crunch the numbers here, and we end up with the amount of time. We just take square root of both sides. Technically, when you do plus or minus, of course, it's plus or minus times are mathematically legitimate or answers or whatever. But of course, in real life, time goes forward. So yeah, you just use the positive one. So we've determined it takes 0.639 seconds to land. So it takes 0.639 seconds to land. And then after that, if you want to know how far over it goes, well, then of course it travels sideways for that entire amount of time, right? And so it travels sideways for that whole time. And so you're really just doing a velocity equals distance over time using the horizontal information, okay? Because this vertical stuff doesn't care that it's traveling sideways, and the sideways stuff doesn't care that it's accelerating vertically, right? So this just works. And so you just multiply out and you get that it would land 3.19 meters over. Exact kind of calculations that Mythbusters would have done to figure out where the bullet's going to land. Okay, and then they tested it out and it worked nicely, of course. Final velocity. So this brings us back to a nice review of how velocities add up vectorially. So the issue you have to recognize here, this is important, you have to recognize that it still has this horizontal velocity of 5, and it has this new velocity of the final velocity in the vertical direction. So that's something we calculate. After we've calculated the final velocity, we need to add them up as vectors. Okay. So first we're going to calculate, it says here, first calculate the final velocity in the y direction. So we use our acceleration, delta v over delta t. We know the acceleration, we know the time. It's very simple to do, right? So we find out that it's going to be going down at 6.26 meters per second. That's the negative is meaning here, right? Obviously, pick equations, but I think this one's easy enough where you're like, just going to use the acceleration equation. This is an old version of the UASM chart thing. Just didn't focus on it here on this page because I don't think it's necessary. So now that we have that, we're going to add those up vectorially. And you'll notice, of course, it's a nice right triangle. So you can just get the size by doing the root of the squares, giving us it's going to be traveling at a velocity of 8. This black velocity there is 8. And then we can get the angle it's at as well by doing tan inverse of the opposite over the adjacent. Works out to the answer of the 6.26 over the 5. So it ends up hitting the ground at a velocity of 8.01 meters per second at an angle of 51 degrees, 0.38 degrees below the horizontal. And so that's it. That's what the calculations with horizontal projection kind of look like. This is the traditional one where you're given the horizontal velocity and the distance it falls. You'll see in the questions here, this is exactly like that. So that's straightforward. This one, just to get you on the right track here, just starting with different variables, right? So notice we're projected horizontally. So basically Vx equals some number, but it's unknown, right? Implied as part of this that it was thrown horizontally, you know that the initial velocity in the vertical direction Vy1 equals 0, Vx1 equals unknown, right? Probably not necessary to label this one as 1 or 2 because it's going to be the same the whole time. But what you do know is that it falls a certain distance. So delta dy equals negative 0.83 centimeters. Convert that to meters, of course. And we know the distance it goes sideways, delta dx equals 18.4 meters. So what's going to happen, just to help you out with this first one, you know how far it falls, you know its initial velocity, plus you know the acceleration in the y direction is negative 9.8. Right, meters per second squared. So obviously you have enough information. You have 3 variables. You're going to be able to get the rest. So from that, you can get the time to fall. And then think about it. If you have the time to fall and you have the distance it goes, obviously you're going to be able to get the x. I just thought I'd try to help walk you through the attack on that one a little bit, because it's not the normal type where you're given the velocity and how far it falls and you just calculate everything. Okay, but a lot of them are like that. This is another one where you're going to have to sort of think your way through it. Okay, so I'm just going to leave that one with you, but keep in mind, I'll just give you a diagram here. You've got a horizontal launch. The ball, eventually lands, right? In between there somewhere, there's the court, the net from the tennis court. Okay, so basically they're asking, like, does it clear and by how much, right? And so you're looking for this distance here. So you'll have to problem solve your way through how to figure that out. Okay, so I think they're a nice selection of questions there of the main type, and then ones where you have to sort of problem solve your way through a little bit. This is a neat example here too. Like if you look at a garden hose and you launch it sideways, you could do this next summer when you're watering the lawn, measure how far it lands and how long that takes to get there. And you could calculate what speed the water is coming out of the hose. Kind of neat that you can do that just by measuring how long it takes to land and how far over it lands. Okay. It gives you the skills to work with these things, which obviously is an important, very obvious, common part of the world around you, right? So yeah, using our physics knowledge. All right, so hopefully that makes sense to you, and we're good to go. Thanks for watching.